Okay, so I guess we're going to go ahead and get started. So my name is Steve Muckle. I'm here to give a talk about the energy-aware scheduling implementation that we've done at Qualcomm. So I guess I'll start out by just kind of saying why we're doing this, what our goals are. As I say, we've developed this energy-aware scheduler, and it's working relatively full-featured, and so we want to see if this work can be used somehow. So I'm going to describe the design that we've got, some of the problems that we faced in developing it, what we think our next steps are, maybe suggestions for sort of community next steps. We understand already at this point, none of this code is upstreamable in its current form. There's no way that this is going to get accepted anywhere, but it can still be useful, obviously, conceptually, to point out things that we need to tackle to get something that's commercially viable for companies like Qualcomm. Yeah, so the design and the implementation are both a work in progress. We're still discovering things and learning things as we go along. So this is the high-level overview. So I'll cover just a really brief summary of the platforms that are driving this development on our end, and some of the scene setting, how we, why we did this development. And then there's 4 major areas that I see that this work can be divided into, and so I'll discuss the issues, our design in each one of those areas, and then I'll cover those next steps. So there's 2 platforms really that are driving this right now from Qualcomm. So 2 chips, both of them are octa-core. They differ really. Well, in the CPU topology, and one has 857s, the other one does not. So this is the lower end chip, MSM8939. So both the chips have independent CPU and cluster power gating. Both of them are internally synchronous within each cluster, asynchronous with respect to the 2 clusters. Yeah, so you can see that this platform, the 8939, has some overlap in the performance range, right? So if you look at the frequency ranges on the little and big cluster, there's a considerable amount of overlap. In fact, the little cluster's frequency range is entirely, or I should say, the big cluster is a superset of the performance offered by the little cluster. So there's a fair amount of overlap here, and I think that that is something that we were concerned about. Supporting well in the software. That's overlap is one of the issues, and I'll talk about that a little bit more later. Closer? Okay. So the other platform that's driving this is what we call 8994. This one is more disparate in terms of the performance ranges offered by the big and little cluster. This is the numbers here are expected to change, the frequency numbers, but right now this is what we're dealing with. So again, similar internally synchronous clusters, asynchronous with respect to each other. So I guess the first question is, why didn't we go with GTS? The initial software solution that was offered by ARM. These are really the concerns why we wanted to roll our own support. So one, is energy-aware scheduling. So we wanted to get the benefits that have been discussed, I think, a lot already here this week, of power-saving benefits. We wanted a more flexible solution that could give us, so runtime power benefits, which I'll talk about later in our power model section. We had some concern with situations where the clusters might reverse roles. So, when we took a look at GTS, it seemed a little more fixed in terms of bucketing tasks and the way that it distributed them on the big and little clusters. In cases where you have significant performance and power overlap between the big and little clusters, we had some concerns about how well GTS would deal with that and whether we could design something that would better handle those cases. So that could arise both out of design in terms of during nominal operating conditions where the chip just naturally, as I say, the first chip that I mentioned, 8939, where there's a significant overlap, you could have that. Or also if you have frequency being throttled by thermal conditions, you might end up with a sort of a role reversal where, say the big cluster is now throttled to a point where it will only offer less capacity than the little cluster. So essentially now the little cluster is where you need to go to get the best performance that you can. So we had concerns about how well GTS would deal with that as well. And then also, of course, there's the upstream concerns. We know that GTS is not going to be a long-lived thing, and so given our other desires for these other features, we thought, why don't we start fresh and see if we can design something that meets all these needs, and also push the development upstream with the features that we know that we need. So the first of the four sort of technology areas here I'll talk about is the load tracking. So as Morten already mentioned, the per task load tracking is a critical piece for energy-aware scheduling. Obviously, the scheduler can't really do anything intelligent if it doesn't know, how much CPU demand a task is exerting. So we know we need to do that accurately. We need to have good per task information. What I think is less clear right now is what accurately even really means. So per task load tracking. What's in the kernel today, I mean, it's a function that takes the history of a task and gives you a number. Per entity load tracking, the algorithm that's in there, well, I'm poaching my own next slide, so I won't do that. Take a step back. So right now, yeah, most big.Little energy-aware scheduling work today uses per entity load tracking. It was added by Paul Turner at Google, so it tracks load via a geometrically weighted series. This feature was not designed for energy-aware task placement or mobile workloads. It was created for, as far as I know, more load balancing improvements, server kind of workloads. And with the default mainline tuning of per entity load tracking, or PELT as I'll refer to it from now on, these are the numbers you can expect. So if you have a task that was, had a demand of 0, so its history was completely 0, and then it switches to be completely CPU bound. As I say, with the tuning that exists today, it will take 75 milliseconds before that task is seen as an 80% demand task. And with the like UI workloads that we have on, say, a smartphone, the desired response that you need to be able to meet task demands of, say, a game, or you pan the home screen, we need to be able to leverage the big CPU very quickly, and bring all of our CPU resources to bear for user-intensive workloads. So responding to transient demand quickly is essential. And a 75 millisecond delay, that 80% is, I picked that number because that happens to be in our energy-aware placement algorithm. That's the sort of up-migrate threshold that we have. So when you have a task that consumes 80% of a CPU, we consider it to be too big, and it needs to be up-migrated to a larger CPU. So that number is not coincidental that I put that there, and taking 75 milliseconds to realize that you need to leverage the big CPU is not going to be acceptable. And likewise, so if the task had been CPU bound in the past, and then it stops and becomes idle, per entity load tracking will decay that to 10% in just 100 milliseconds. That again, I mean, it's an open question of whether that kind of latency is that too fast, and it's going to do this regardless of what else is going on in the system, what kind of task it is. Do you want that task to stick around on the big cluster so that it can immediately leverage the big cluster when it comes back and runs again? So I talk about this heavy task at the bottom here. So a good example of this might be a web browser or a game. So it's very intensive, and then the user stops touching, say, the screen of the device, so the task sleeps. But it's waiting for user input, and as soon as you do something, it's going to need all those resources again to immediately respond and render some more frames or whatever. And so you don't want to incur that latency again for it to, for the scheduler to realize and learn over another, say, 75 milliseconds that it needs to use that big CPU, right? So we saw a need to maybe ignore periods of idleness. But this is clearly this is very heuristic based, right? This is learning how to, what sort of demand number should you associate with various patterns of task activity is not a straightforward task. So, I mean, I see the load tracking mechanism as, it's an algorithm that it's not clear what the right algorithm is. per-entity load tracking, which is in the kernel today, it is not an absolute representation of task demand over any fixed amount of time, right? It's what it is. I mean, it's, as I say, it's a geometrically weighted series, which, as you go back in history, it treats, if you divide it all into 1 millisecond buckets, it will treat, as you go further back, each of those buckets has less, weight on the demand. What you end up with is it's not a discrete, when you have window-based tracking, like in CPU-freak governors, you can say, okay, in this 20 millisecond window, we knew we had exactly this amount of execution. It's very easy to reason about what that is, right? What that means. With per-entity load tracking, it's not quite so much. I mean, it's more of a nebulous, okay, long-running average. And so translating that into what we should do in the scheduler or with frequency, I think is less clear. So this is just a little graph of if we had a task that ran for 20 milliseconds and then slept for 20 milliseconds, that duty cycle repetitively, this is the demand that per-entity load tracking will report. And I don't know that I really have a specific point here other than just sort of raising the question of, is this what we want? I mean, you're going to have, is this right for CPU frequency management? I mean, a task that runs for 20 milliseconds showing up as, less than 50%. If you just look at the very first part of that graph, it ran for 20 milliseconds and it showed up as, at the end of that run, it showed up as like 36% or something utilization. Again, I mean, in mobile workloads, that's probably not going to be good enough. I mean, I think most, like the interactive governor today, which is used on most Android devices, it's going to ramp up. If it sees 100% demand, it's going to shoot to high-speed freak or, some other configured high frequency. And when we have big.Little placement or energy-aware placement, it's kind of an extension of frequency guidance, right? I mean, it's on that same scale. We need to now not only know the right frequency to go to after we see task demand, we need to get the CPU placement right as well. And we can't afford to stack latencies together. We don't want to take longer to figure this all out before we meet a task's CPU needs. So, yeah, so this graph is really to just kind of raise that question. So what we did, I mean, after seeing these issues, I mean, we tried some tests with per-entity load tracking, and we had the concerns that I mentioned, and so we decided to try out a window-based approach to load tracking. So I'll just cover this at a high level. What we're doing is tracking the n most recent non-empty windows of task demand. So both the number of windows of history that we keep and also the window size are configurable. So for the purposes of this discussion, let's assume 5 and 20. And then we calculate the demand based on these samples, and you have some flexibility in the policy that you use to calculate that demand. So, we support a few different things, such as averaging the Windows samples, taking the max or this max of the most recent sample and the average. So, and I have some examples of the numbers that you would get. So, if you had a history of task execution that looked like this with these numbers, now again, you could have had windows interspersed amongst these 5 that were completely empty, but they wouldn't be shown here because we dropped those. So with those same numbers, these are the task demands that you would get using each one of these different policies. So it gives a little more flexibility in terms of and each one of these things is going to give you different behavior, right? If you use it for say big.Little task placement, taking the max is going to obviously be very aggressive, whereas an average policy, not as much. Max of recent and average is what we're running with internally because we like the responsiveness of that. When you see a lot of demand all of a sudden, if there's a large value in the most recent window, you want to react to that. But then at the same time, you don't want to, as soon as that large value moves out of that most recent spot, you don't want to immediately, say, down migrate it. You want to rely on the average to sort of smooth out that transition back to the little cluster. So, but overall, we found that we like the flexibility that this gives in terms of experimenting with different options and coming up with that algorithm to turn task behavior into a demand value that you would then use for task placement and also potentially frequency guidance. So, let's see. So a little bit more about the implementation that we had. So the windowing feature that we have is aligned across all the tasks and all the CPUs. So this helps with the scheduler guided frequency that we're doing, and I'll get into that a little bit later. That assumes that we have a synchronized sched clock. We're using sched clock for the window boundaries. So the load values that we take, they have to be normalized, so that's been discussed already, and I think is in process of implementation with the work that ARM and Lenaro is doing. We have to normalize it, so we normalize it to both the maximum frequency and the max IPC, so that's the microarchitectural differences that Morten alluded to. And when we normalize those values, you assume no thermal throttling, so we're using the maximum frequency supported by the hardware. And so, this is the equation that you would use to calculate the normalized demand. So if I see, well, I have an example, I think, on the next slide. So. Sorry?
What do you mean by line?
Oh, by a line. So what do I mean by a line? So aligned windows, that just means, so the windowing that we're using to measure task demand, those window boundaries are the same across all CPUs. So. What do I have? So yeah, so if we consider this example topology, so this is like saying what we might have on our 8994 platform. 2 gigahertz Fmax for the A57, 1 gigahertz Fmax for the A53. So obviously the A57 is our highest capacity CPU. Also the microarchitectural differences, the A57 we estimate has, say, a 2x IPC compared to the A53. So if we have 10 milliseconds of task demand on the A53 running at its Fmax of a gigahertz, what would we record that as for that task demand? And so you see, you have to take into account the fact that the A53 is slower in frequency than the largest CPU in the system. And then you also take into account the IPC. So that'll actually end up getting recorded as 2.5 milliseconds instead of 10. So.
Have you measured any potential overhead for the window tracking in the scheduling decision?
No, we have not. So there's some rumors, unconfirmed, that maybe there's some overhead associated, not just with this, but also when I get into the modifications that we made to the scheduler and the load balancer, all of that stuff, we have done no performance impact analysis on it whatsoever. I don't think that I don't think we have any reason to believe yet that it's significant enough to be a problem. I think when compared to Perenity load tracking, I don't think it's, at least in terms of the operations, like the math operations we're doing, the lines of code, it doesn't leap out to me as being suspect. So, but no, there hasn't been any conclusive testing done. So. So, as
can I ask a couple of questions?
Yeah.
One is, which you probably mentioned and I missed, but when you're saying you're aligning, does that imply that you have a periodic wake up on every single core?
No, we don't. So yeah, so we do not have a periodic, any sort of tick or periodic activity to measure that. We just, when some activity happens on a run queue, we can look at the sched clock. We know when, we know when the activity is. We can jot down when the last event was for a task, and we can divide out. We know what the windowing boundaries are, so we can divide the demand into. Okay, we know this was in the last window. This is in the current window. Yeah. So we avoid any sort of periodic check.
So one of the primary differences, it seems like, is the what you call it, non-empty windows. This takes a couple seconds after you turn it on. It was already on.
I think it's running out of battery.
So I'll just talk really loud. So it seems like one of the big differences is the non-empty window, which essentially means you're not considering any idle time.
Well, not any idle time, right? Because if you have a 20 millisecond window where the task ran for, say, a millisecond, then you will use that window. So you'll get the idle time surrounding that. It's only if you have an entire 20 milliseconds where the task didn't run at all. So I agree that is somewhat arbitrary, but I mean, this whole thing in some sense is a heuristic. And I also admit, I mean, that is something that we could probably add back into Perennial load tracking. I'm sure we could add in some kind of tunable to say, you know, when you're updating the Perennial demand value in PELT, you know, ignore an update that means you're going to have more than, say, 20 milliseconds of, you know, of idleness. I think, you know, in addition to the this ignoring idle windows thing, we also wanted the flexibility of the other policies, you know, this sort of plug-in-y kind of architecture for the policies to apply the window values. So as I say, all the demand values are going to get recorded, normalized to the highest capacity CPU in the system. So when you want to use those values, you know, if you're doing operations where you need to know how that load would appear on a certain CPU that may not be the highest capacity CPU, you need to translate that back, right, into what that would mean for that CPU. So we use a value called load scale factor for that. So the load scale factor, it's just a multiplier that will get you back to what that demand you know, would be. And when you're doing that, that now needs to take into account the fact that the max frequency on that target CPU may have been throttled by thermal. So you know, in the calculation for load scale factor, you're going to use the CPU's current Fmax, not necessarily its max possible frequency that would be allowable by hardware under nominal operating conditions. So I have another example here. So if we use that same topology that we were considering before, and we have 5 milliseconds of demand, say we had a task that ran for 5 milliseconds on the A57 at Fmax of 2 gigahertz, because that activity would actually result in the demand value for the task showing up as 5. Now let's say that migrates to, or we're considering migrating that to an A53, where the A53 is thermally throttled to 800 megahertz. What load would we consider that to, you know, what would our estimation be for the load of that task on the A53? So I won't just read the math that's here because you can look at it, but you know, you end up with 22.5 milliseconds, which, you know, is actually over 100%. But you know, that's how that would work. So
can you just come back on the previous slide in the way you are computing the value? So you speak about the CPU current frequency max. When you are tracking the load with your non-idle windows, do you take into account frequency scaling in the middle of these windows, and how do you take that into account?
Yeah, so we register for notifiers from the governor or from the CPU free framework, and then we always write down the frequency that a CPU is running at in its run queue in the run queue data structure. So whenever we're attributing load, you know, for a task, we use whatever the current frequency is.
Okay, so when you have a change, when you change the OPP of a CPU, you have to update all the run tests, the load tracking of all the. I mean, when are you updating the load tracking?
Yeah, so when that notifier, when that notifier comes in, I mean, you only have to update it for the guy who's actually executing on the CPU. So you need a notifier on every CPU that's affected by that policy change, or you know, the frequency change. And when that notifier comes in, you know, the window-based load tracking, it considers things kind of in segments. You know, you have segments of execution and segments of idleness, or not idleness, but not running. And so when we have a frequency change, you're basically breaking that single segment into 2 segments. You know, you end your current segment at the frequency that was, you know, that used to be the case, and then you'll start a new segment at whatever the new frequency is. And you use the notifier as the opportunity to do that. Okay. So,
just so you are tracking the running time and not the runnable time of all the tasks.
So, yeah, I wasn't going to get into that in this presentation, but yeah, we have played around with doing both of those things. You know, we had a large internal debate that I don't think is even really settled about whether to track runnable or running time. In short, I think runnable time ends up showing values that are just too high. I'm not sure it's the right metric, especially for frequency guidance. It's definitely the case that. You know, today the interactive and on-demand governors, they work on running time, right? They work on how much was the CPU you know, idle, or how much was it actually busy. So yeah, moving to runnable time, we basically have to retune the governor, right? Because it's a very different set of numbers you'll get from. So. Charles, did you have?
Yeah,
sorry.
so I can shout. If you have a test that's effectively taking up 100% of an 83, so it's goes up through the roof. Sorry, I'm not shouting. If you have a task that's taking up the whole A53, and then you migrate it up to an A57, does that suddenly 100% become a 50%?
Yeah, it will. So, yeah, I mean, so if it was 20 milliseconds on an A53, which in our little topology here would max out at 1 gigahertz. The system F max is 2 gigahertz, right? So that's going to have it right there down to. So it'll actually show up as 25% because on this topology, right, the IPC is also there.
Right. It's just yeah. It's just kind of it might make sense to make that an exception, right? Because if it's taking up CPU entirely, you have no,
Right,
you're just completely take up the A57.
Right, yeah, you're losing information.
No idea.
Yeah, you're losing information. You've clicked to the top because you don't know. So, I guess that's a good question. I mean, how much more? That's another opportunity, I think, for a heuristic to come into play. I think the hope is that the tuning that we have will up-migrate tasks. Hopefully the task isn't starving long enough on the A53 such that you haven't lost so much information. If you can respond fast enough, but we're still tuning. So.
There's another question.
So couple of them actually, back to back. So, I mean the LSF or normalization you said is a pretty good idea, but I was just wondering, how do you do the aggregation for a cluster actually? I mean, because you said you're maintaining the windows per CPU. So do you consider the cluster aggregation and loading the cluster instead of moving to the?
Well, I mean, as far as unless we're talking about frequency guidance, I don't think there's really much to say about aggregation. And when we were just talking about, so here we're really just talking about load tracking for the task. I mean, I can get more into the modifications we made in the scheduler as well as the frequency guidance later. I think the only real sharing of information you need between CPUs, it's not even really relevant to clusters per se, but is the alignment of windows. So, we need to communicate that window start value. Like when this algorithm gets going, you need to make sure that the window start value is known across the whole system and communicated to all the CPUs. So, yeah, I mean, for the scheduler guided frequency, which I'll get to a little bit later, you do need to aggregate the demands, and there is the issue that, if you have an internally synchronous cluster, your recommendations to the governor may want to take that into account. I mean, that might get aggregated on the CPU freak side, or, do you want to waste time notifying the governor if you see a CPU in a cluster that's under provisioned, but there's another CPU in that same cluster that's the one that's driving the demand. It's not worth notifying the governor in that situation. So then we had to start adding in knowledge about, okay, these are the policies, this is the CPUs in the CPU freak policy. Don't bother notifying the governor if another CPU in this policy is the one that's driving demand and I don't have anything going on. There's no word, you don't bother, telling the governor to slow down. But yeah, just for this, there's really no aggregation or topology considerations.
Okay.
Let's see. So yeah, I covered this. Okay, so I'll move on to the power model. This is a fairly short section. So just to kind of set the table, I mean, obviously Morton and Dietmar are working on a power model, an energy model. But ours is a little bit more simplistic, so we don't real high level comparison. So we don't do any wake up rate measurement. They do fancy measuring of the expected wake up rate of the task and tracking what the wake up energy cost is, and that's included into their costing data. They also consider if I place a task on a CPU in a synchronous cluster, and that's going to elevate the frequency on that CPU. What is the additional cost that's now imposed on the other CPUs in that same cluster because the frequency of that cluster was raised, right? So we don't do either of those things. But the one thing that we do, that we are doing, that I hope to see make it into the upstream implementation is that we support the power numbers changing at runtime. So you know, the desire for this comes from you know, at runtime, you've obviously, the thermal conditions are changing constantly, and if you're running a CPU-intensive workload, the temperature of the core, the various cores in the SOC are gonna change, and that's going to impact your power numbers significantly. And so, you know, we are already seeing in our testing, we're seeing benefits from taking that into account. You know, and you want to seek out, you always want to be running on the lowest power core that's going to meet your needs, and thermal will have a significant impact on that. So we have a very simplistic implementation to get us to this point. So I mean, this is our very basic pedestrian API for this. So we have a power driver which can register with the scheduler, and then we have this callback that we can call from the scheduler to get power data. So for every CPU, we'll get a table that contains, for every supported frequency, what is the power cost for the sort of a milliwatts per MIPS number for every frequency supported by that CPU. So, you know, this is what that will look like. So when I call that API, I'm going to get this data back, and I can then use that to make intelligent decisions about where to place my task, assuming I have an idea about its CPU demand. So I'll move on to the HMP scheduling stuff that we did. So just to summarize the information that we have available now, so we'll have good, you know, hopefully good per task CPU demand data. We have the power data that I just mentioned. We know the current and the max frequency for a CPU, as well as the max possible frequency supported by hardware, and then the other information that the scheduler is already tracking, such as the number of runnable tasks on every run queue. So some definitions to our HMP scheduling algorithm. What is a small task? So, you know, we want to treat small tasks differently. I know Vincent's already done like small task packing stuff, and they deserve special treatment. So we have a tunable, we've defined a million tunables, so another reason why this will never go upstream. But we have our sched small task tunable, which defines, you know, as a percentage of the lowest capacity CPU. If your task consumes less than that, then it's defined as a small task. And we're going to treat that differently, and I'll get to that in a subsequent slide. What is a big task? So this, as I mentioned earlier, if a task consumes more than this percentage of a CPU, then we consider, okay, it's too big for this CPU and we need to upmigrate it and find a CPU with higher capacity. Mostly idle. We created this because we saw a need for, you know, maybe you don't always care about placing a task on an idle CPU. Maybe it's okay if that CPU has, say, a little bit of load. You may miss out on potential opportunities to save power or other good scheduling decisions because, you know, maybe there was some tiny task that happened to be running on the CPU at the time. So we wanted to give you to give a knob to kind of say, okay, how busy will you let a CPU be? You know, what kind of slop are you willing to tolerate when you're trying to find a good CPU to schedule on? And then the last one, the spill threshold. This basically controls how much are we going to try and pack a cluster before we spill over and use another cluster. So, you know, let's say that you've got a whole bunch of tasks that take 10% of a CPU in the little cluster, and these tasks keep waking up. So, you know, initially, you know, you can start scheduling them on CPUs in the little cluster. At some point, that little cluster is going to be busy enough where you want to start asking the big cluster to help out. When that point is not clear, right? That's going to depend on the power cost of these two things, what your power power budget is, what your latency concerns are, and so yeah, this set of tunables gives you a way to do that. So actually, both the mostly idle and the spill threshold concepts have both NR runnable and percent busy aspects to them. So you can specify both of those things for both of those tunables. So, you know, the code to implement this is quite complex. I didn't want to bother with a flowchart or any code here, so I'm just kind of gonna give the end results of what our algorithm, you know, the behavior that it does. So, in the wake up path, you know, I guess there's kind of two primary places that our scheduler modifications were centered in. So one is the wake up path. We have lobotomized the current wake-up path by just going into select tasks run QFare, and we just call into our own special thing and hacked out, just got rid of the whole wake-affine code and balance on wake and all that stuff. So this is all we're doing. So a non-small task wake-up, our first preference is a least loaded CPU, as I say, where the task will fit in the smallest cluster. That's going to give you the best power. And you don't want to cross the spill level, and then when you have CPUs that are a tie in their load, we use the power cost to break ties in the load. So, it may look, well, the power cost seems to play a fairly minor role here, but that's a case where we expect to hit that a lot, because in most times you're going to have 2 or more CPUs that are idle. And so it's going to be a very common case that you're going to come down to, okay, I have a selection of multiple idle CPUs, which one do I want to choose from? At least that is the case for most of the workloads that we look at. So that's our first preference. If we couldn't find any CPU that meets that criteria, so essentially maybe there is in the smallest cluster where the task will fit, maybe it's full. Maybe there's nowhere to put, there's no CPU where adding this task would not cause the spill threshold to be crossed. Then we fall down to our second option, which is the least loaded, mostly idle CPU where the task doesn't fit. And then if we can't, if we can't meet that, then we end up falling back to just whatever the last CPU is that the task ran. So
speak that power cost.
Mm-hmm.
That power cost, does it take into account cache costs, waking up other clusters?
It does not. Right now, it is solely based on the CPU's. Well, okay, yeah, I'll just say it does not. So for small task behavior, as I said, it's a bit different. So with small tasks, we wanted to avoid waking up CPUs that were in deep low power states. Obviously you don't want to pay the latency and energy cost to bring a CPU out of, say, a power collapse, just to run something that's gonna execute for maybe half a millisecond. So so this is the order of preference for small task placement. I don't know how in detail I should go in here. I'm not going to read it out. But essentially we're trying to prefer CPUs that are already running but have a very low load. So and again, I mean, there's room for debate here as well. I mean, it's you kind of have a decision. Do you want to pay the latency cost of coming out of a sleep state on a CPU, or do you want to pay the latency cost for waiting for some other task activity to complete on a run queue, or impose latency on some other tasks by waking up a CPU, on a CPU that's busy? So this is the design decision that we've made for now, and as we're still kind of evaluating it. So. So in addition to the wake-up path, one place that we made another modification is the scheduler tick path. So we had concern over CPU-bound tasks, the behavior of CPU-bound tasks. So a task that never sleeps is never going to come back through the wake-up path for us to reevaluate the condition of the topology and perhaps renew its placement. So it could be the case that when we placed a task, it was very low demand. For example, when you start up a new task that has no history, your initial task load might have been 0. Maybe you had your initial task load defined as 0, and so you placed it on the little cluster, and then it never went to sleep. It's just completely CPU-bound. So we needed another place where we can reevaluate the placement. Also, the power conditions may change. So maybe the task is already running on the big cluster, but the core that it's on is heated up because you've got a CPU-bound task there. And so now there's another big CPU that's more efficient. So yeah, the tick was where we put that. I think that we're looking to get rid of that at this point. So after our modifications to the load balancer, which is the next slide. We've had to extensively modify the load balancer to retain the policy decisions we make in the wake-up path. So energy-aware scheduling is not really compatible with what the load balancer is doing today. It's for a number of reasons. One is that the load balancer is designed to spread load, right? And it's also working on this primarily on this priority weighted load. So the metric that it's using it's using a different metric to achieve a different goal. And so, we've made changes to most of the load balancer functions to try and preserve the policy that we've created in task wake up. So I've given a small summary of when we'll migrate tasks between clusters. So like migrating from little to big, if the little cluster, if we have a CPU that's beyond its fill threshold, or if there's a big task on the little cluster, obviously you want to up-migrate that. Going the other way, migrating tasks from big to little, so if you have an overcommitted big cluster, so you have more big tasks than you do big CPUs, then you want the little cluster to help out. And then power-aware scheduling, so when we're doing balancing within a cluster, if we see if the CPU running the load balancer is more power efficient, and it's than another CPU that it sees is running a task, then it should pull that task over to save power. Yeah, so active balance is something that we're doing a lot more now. So the active balance path was not something that happened very often in the load balancer, but we rely on it quite a bit now to help retain our policy.
So Steve, you talked a little bit about how you may move work around based on changing power efficiency of different cores, presumably due to thermals. Do you find that you're able to react quickly enough that the temperature isn't changing faster than your interval, you're not just chasing your tail?
We haven't really had an issue with that. I mean, at least, so our internal testing, yeah, we haven't seen an issue. I mean, if you let's say you're running a CPU-intensive task on CPU 4 and 857 and its temperature is increasing, I mean, it's not going to get rectified until you schedule that task somewhere else, presumably. I mean, if the other CPUs, I mean, the only situation I guess I can think, I mean, if something else happened to get scheduled at the same time that you decided to move it somewhere else, maybe that's what you're...
No, I mean, I was getting in a case where, let's just say you have one task, right, and it heats up this core, so you move to this core.
Right.
Does the sampling rate of how quickly you're evaluating the temperature move back and forth actually faster than the thermal time constant, right? Or the second you move it up there, this guy gets hot and this guy gets cold and you just end up ping-ponging?
Yeah, so the ping-ponging thing, getting the granularity right, yeah, that is something that we've discussed and I think is an open issue. We're already seeing gains, so it's clearly not a showstopper, because we're already seeing value out of it. But I agree. I mean, we were not sure that the numbers that we're getting from the power driver, how granular should they be? What's the threshold that you should see difference before you decide to move that task over? And that's like comparing it to the migration cost tunable that's in the scheduler today. They already had a notion of how expensive is a migration, and yeah, that's a tuning exercise that we're still working on.
Hi. I don't know how thermal plays any role in changing the max frequency on the cluster, but what happens if the big cluster becomes suddenly small because it's thermally limited?
Right.
Do you evaluate all the tasks on both clusters, or?
Yeah. So I mean, the functionality that we have to evaluate whether a task will fit on a CPU takes into account the current Fmax of that CPU. So yeah, I mean, this implementation, if thermal throttling causes the big cluster to say be limited to 500 megahertz, and it is now smaller in capacity than the little cluster, this will do the right thing. Basically, the wake-up path and the load balancer path will now start treating the little cluster as the big cluster.
But do you migrate as each task comes to reevaluation, or do you trigger the whole?
Well, so I mean, initially when that event happens right away, I mean, yeah, it's going to take, I mean, if everything is, say, CPU bound, you're going to be relying on the tick and the load balancer to move those things over. I mean, basically the next time you have a scheduling event, either the task is waking up, then it will respect the new situation that the small cluster is providing the most CPU bandwidth. Or when the load balancer runs, if you have tasks that are CPU bound, the load balancer will do what it can to rectify the fact that now the little cluster is the biggest. So I don't know. It looks like I didn't answer your question because you're still.
Well, I'm trying to figure out what happens if let's say you have run a couple of CPU-intensive tasks on the big one that heated up. So all of a sudden you have a very aggressive thermal protection. So you suddenly the big one becomes half the speed of the little one. But the little one is quite busy having small little tasks. So you're trying to spill a big task into the little one because that one becomes big. And I don't know how much going around is going to happen.
Yeah, I mean, if the little cluster is already busy with work, then I mean, you just have an overcommitment situation in general. And I mean, the load balancer, I mean, we will try and do the right thing. I mean, we're not just going to, mindlessly shunt all the big tasks over to the little cluster if the little cluster is already busy with other work. We'll do a comparison and see whether they will fit. I mean, we do try and do load balancing still. I mean, we will try and smooth out the load. Maybe we can talk more after the presentation because I still have another section. So I think there's just 5 minutes.
Just one question. You just say that you have much more active load balance. It's when you mean active load balance, it means that you start the stop task to actively migrate the last CPU, the last task on the CPU. It's another meaning, just to be sure.
Yeah. So we're using the active migrate. The stopper task comes up and forces basically we want to migrate the running task off of a CPU that's only got a single task. So.
Okay.
The last section I wanted to get to was scheduler guided for CPU frequency. So this is something that we're still kind of working on, and I don't know. It's not really clear yet, I think, in practice, the results that we'll get out of this, but there are theoretical problems that arise from the way the CPU freak operates, the fact that it doesn't have knowledge about per task demand. So there's 2 problems here that I wanted to talk about. One is when a task migrates in the middle of a window. So what is this diagram? So this is say, the 20 millisecond window that interactive or on-demand is operating on. These red dots are when the governor is running at the end of the window on that CPU to evaluate the frequency on the load that it's seen. So in this situation, we had a task A, maybe we'll call it, which ran on CPU 0 for 10 milliseconds, and then in the middle of the window it moved to CPU 1. So each CPU is going to see 50% demand, or 50% idle in this case, and depending on how your governor is configured, maybe neither one is going to see the need to ramp up. And that's a problem, right? Because now, I mean, CPU1, let's say this is a CPU-bound task. CPU1 has a CPU-bound task on it, but it did not ramp up its frequency to deal with that. So that's one issue that we wanted to fix. The solution that we saw was to basically, we're doing the aggregation of load. I forget who asked about that, but yeah. So aggregating the per task demand in each for the previous window on each run queue, and providing that to the governor. A little bit more on that later, but basically when that task migrates from CPU 0 to 1, in the current window, its load will move with it, and so we'll subtract its load so far that it contributed from onto CPU 0, and we'll move that down to CPU 1. So now, when the governors run, CPU 0 will see 0 demand, utilization, assuming nothing else ran, and CPU 1 sees 100%, and it'll respond and increase the frequency. So that's an issue with load moving around in the current window. Here's another issue where it can be a problem. So if we had something that, say, used the entire previous window on CPU 0, CPU 0 then sped up, and then right after that next window begins, that task migrates to CPU 1. So nothing ran on CPU 1 in the previous window, so maybe the governor ramped it down to Fmin or whatever. So this is a really bad situation right now because CPU 0, it's going to be idle for the rest of the window needlessly, and so you're potentially wasting power there. CPU 1 is running at potentially some slow frequency, and it's not going to ramp up for another 18 milliseconds. So this is where, if we do the right thing, when that guy migrates, can we migrate? What happened here? Yeah, so if we migrate the load of the previous window along with that task, and then provide a notifier, so we can notify the governor when that task migrates to CPU 1. We can check to see when we change in set task CPU, we can evaluate and see whether the CPU is now very over or under provisioned, and notify the governor. We're not taking control of the frequency completely. We're just basically telling CPU freak, hey, you might want to reevaluate things because there's been a big change. So a little more on how this is implemented, and I'm just almost out of time. We really wanted to maintain the CPU-free governor policy, so I'll take the fact that I have the mic right now to voice concern about getting rid of the governor. There's been discussion about that, so we really wanted to keep interactive around. It's what a lot of folks are used to, and they're used to tuning it and the policy associated with it. So we wanted to minimize the changes to that. We provided a couple of APIs to allow interactive to leverage the knowledge that we have in the scheduler. So the interactive governor, it needs to set the windowing policy that the scheduler is going to use, because interactive is still setting timers. It's still making assumptions about what the window is. So the window needs to be the same in the governor, or the understanding of the window has to be the same between the governor and the scheduler. And then we provide a new API to get the busy time. So interactive uses a simple API to get idle time right now per CPU. We basically just replace that with a call into the scheduler. This getBusy API is going to return a fixed up value that takes care of the problems I mentioned, the migration issue. And so that allows us to have a very small delta against interactive to fix these problems. And then, as I say, governor gets notified when the scheduler sees big demand increase or decrease. Knowing when to notify the governor is not simple. It turns out to be a fairly hard problem. As I mentioned, there's issues with the topology. You might flood the governor with needless notifications when it can't do anything. So that turns out to be not simple.
So the periodic timers are the reason why you're seeing those problems, right? The migration of task in between the window. So why do you want to retain that?
Because I'm not convinced that the geometric series approach of PELTs is going to work out, I guess.
No, what I meant was with what the work that Mike's doing, we're trying to, because it's event-driven, the task migration is sort of kicking off the CPU freak event as well, right? So
I think the point is that the statistics are updated somewhat instantly, right? Since you're not using like a bucket or a window, then you don't have to go and like fix up statistics after the fact.
Yes, yeah, so I'll agree that, I mean, this approach certainly has its inefficiencies, and I mean, you're essentially having to maintain two separate windowing schemes and make sure that they're the same. I guess right now I think interactive is a place for us to put hacks and heuristic tweaks for frequency management, and that's kind of I think that's my concern about losing that place.
So on a related note to that, because I definitely understand having a nice set of call sites to do hacks and tweaks and to experiment, would you say that like playing with the geometric series and the decay values and things like that, would you like that to be easier? Because I mean, those, if that could be more tunable than it is today, would that be of interest to you?
Yeah, if there was some kind of sort of, in the way that we have governors, if there was, I think this algorithm of measuring task demand based on a task's history, I see that as a very similar problem to the governor problem. It's some kind of algorithm. It's some sort of heuristic algorithm about what kind of demand am I going to associate with a task that had this history versus this history. I think the algorithm for that Paul Turner might want to use for load balancing on giant servers is probably not going to be the same as what we want for mobile workloads on smartphones. So it's not clear to me that there's one correct answer for that, and having some sort of plug-inable or governor-like thing where we can select between different options, or at the very least, yeah, make it easy for people to experiment and provide different solutions would be good.
So I guess we should allow people to take a 5-minute break and have.
Yeah, I'll just, while folks are on their way out, these were the next steps that I saw. So.
I use 2.10.